Welcome. This is the last lecture of thermoelasticity, where we have planned to solve some of the examples of thermal deformation or thermal stress. So, here what we have done is we started with a general thermoelastic deformation, or specifically we have derived the energy equations and showed that the uncoupled form of the thermoelasticity, which again we have extended for plane stress and plane strain formulation. We finally used some well-known approaches like stress function and then displacement potential function, and then derived the biharmonic equation for the plane stress and plane stress case. So, here in this lecture what we will do, we will study some of the simple cases of thermoelastic deformation, where for instance let us consider a thermal stresses in a thin plate. So, consider a rectangular thin plate, and then with uniform thickness, but the interesting thing is, let us consider the temperature profile is a function of y only. It is not a function of x and z, and that leads to actually the thickness direction stress is constant. Basically we can invoke the plane stress condition. So, now if you look carefully, that if I want to find out the thermal stress along x direction, considering that y direction is free. So, if you increase or if your thermal profile is Ty, then the y direction is free to expand. But if I try to resist in the x direction stress, or the compressive stress essentially required to keep the plate from straining in x direction. So, if I just keep this direction, if I am not allowing this direction to freely expand, then the compressive stress essentially alpha E and T, essentially delta T. So, T y is my temperature variation. Now, this is this stress sigma xx dash is varying along y direction, because this temperature profile is a function of y. Now, similarly, the plate will experience thermal stress. So, the thermal stress, that is tensile, obviously the opposite stress, this stress will be generated in the plate, has to be integrated from minus C to plus C, and then for if we divided per unit thickness, then this stress is integral of this quantity into dy, because temperature profile is variable in y. Then per unit length, unit thickness of the plate, or unit width of the plate. So, now these two stresses, sigma xx and sigma xx sigma xx dash and sigma xx double dash, should be balanced. So, that is that we can do in with the help of principle of superposition. So, now using the superposition, I can write this must be the total stress along the x direction. So, now if I put these two quantities, so this looks like this. So, this is my total stress in the x direction, which actually needs to be equilibrated. Now, there is also an effect of, you have probably known this thing for a from previous discussion, that this is the at the end of the member there is a effect, end effect, which we called. So this stress is naturally not valid at the end of the body, because we have so called Savena effect, which is the end effect or the boundary effect of the system. So so if it is sufficiently away from the end of the end of the body, then we can express this sigma xx as this. Now it is interesting to know, if you have this alpha E Ty, so if you know the temperature variation, how Ty is varied along y, and so you can find out this stress and you can compute this stress at any cross section. So now let us see, let us assume some of the stress, some profile of the temperature essentially, and then let us see how it looks like. So let us now consider the temperature varies parabolically. So it's a parabolic equation or something like that. So now T0 is a constant temperature, and then how it is varying along y. So if you now put this Ty and integrate into this equation, then you get this expression. So which is again a means variable in y square. So if you see, that means the temperature, the stress along this body varies along y square. So this, from which we can calculate where the maximum stress occurs and where the minimum stress occurs. So suppose at y equals to c, that means at the surface, then this the value, if I write, so this quantity goes to 0. So this stress is actually the positive stress or the tensile stress here in the body. So this is 2/3 alpha E T0. So this stress we know. Now if at y equals to 0, then this is 2/3 alpha E T0 minus alpha E T0. So this is now again the compressive stress. So because this quantity is greater than the latter quantity is greater than this quantity. So this is essentially 1/3 alpha E T0. So now this part, so this is this part essentially, and this is this part. So now we can see this is the negative part, and this is the positive part of the stress. So this way we can find out the what are the stresses in the body. So if we assume the temperature profile in this parabolically, what will be the stresses in the body. So this is a very simple example by which we can understand the how temperature creates actually the variation. Now here it is important to know that this when we apply the principle of superposition, we have applied only for the stress or the force actually, because this is the temperature profile. If you look, it is symmetrical about the x-axis. So that means this function is an even function. So now if this is unsymmetrical, now this temperature profile is unsymmetrical, then you have to consider the couple also, the couple balance also you have to form, and then you can equate with the equilibrium, and using principle of superposition, then you can find out the what are the stress. So I recommend this part you can also go through in the Timoshenko book, where the thermal stress chapter, this is already derived in there. So this you can follow later. Now, let us consider some of the other problems where actually we need to understand, or the problems are little more complicated. So, say instance for a thermal stress in a thin circular disc. Now, this disc is centered at the inner radius, say it is r equals to a, and outer radius r equals to b. Then in the again, if I assume that temperature profile is a function of r only, so there is no theta dependence on the temperature. So then again, since the disk is thin disk, we can assume again plane stress condition, and then if we see that only sigma rr is the quantity that will actually be non-zero, but since the deformation will be symmetric, this quantity, that is sigma r theta, will be 0 essentially, and then sigma theta will also be there, but sigma theta will be a function of r only, because there is no variation of the temperature in the theta direction. So because of this assumption. So now if you assume in the polar coordinate system what is the governing differential equation or the Navier's equation, then you get these quantities, the red quantities are already 0. So only this quantity and this partials becomes a total derivative. So this becomes this equation. So now similar to our previous case, we know the strains in the polar coordinate system. So this there will be u, the radial displacement, and the theta direction displacement is v, which will be 0, because the v is not a function of theta. So if I write now this quantity, so this will be the standard compliance relation that we know. So only the thermal strain part is added. Now similar since the r theta is 0, so and so this quantity will be 0, and this quantity again u will be function of r only, because from here we can see that u is a function of r only. So this quantity goes off, this quantity also goes off, and this quantity also goes off. So essentially shear strain is also 0, because it is a symmetric deformation. So there will be no shear strain generated. Now if we now put this compliance relation, that is epsilon rr and epsilon theta theta, and then find out what is the constitutive relation or the stress strain relation, and then again we can substitute these sigma theta theta and sigma rr into our governing differential equation. Then we can get a final differential equation which is of in terms of u and v. Only in terms of u. So let us see what is that. So this does not become partial now, because u is a function of r only, and then we write the final expression for the strains in radial direction and then theta theta direction, and then we obtain the constitutive relation, assuming that plane stress condition. So this quantity is my final stress expression. So you see this is very similar, this thermal strain that we have discussed, that will come into the stress expression. So now if I substitute epsilon rr and epsilon theta theta here, the stress components looks like this. Now if we again substitute here this equation, then this equation becomes a second order partial differential equation. Now if you look carefully, this type of differential we have studied earlier. So this is a simple case, but this type of deformation we have seen in terms of displacement potential function. So if you remember that this displacement potential function, this del psi, this equation is very similar to this equation. You see, this is for plane stress condition. Now what we did actually there, we integrated this equation into and make it one single equation. So here before that integration, this equation is very much similar in the polar coordinate system. This is in the Cartesian coordinate system. Now, the fact is we are following the same approach here. So, now how to solve this equation. So, the solution of this second order differential equation we can easily obtain by this, and the solution is of this form. So, here the displacement is a function of r only, since we do not know what is the profile of t. So, that integration we cannot perform. So, it is a function of tr only. So, now there is two integration constant and C1 and C2. So, now if I write my stress quantities sigma rr and sigma theta theta, then these stress quantities will be in terms of C1 and C2. Now, since this C1, C1 and C2 we have to find out from an appropriate boundary condition. Now, based on certain boundary condition we can find out C1 and C2. For instance, if there is a solid disk, the disk is solid, then there is a boundary condition, and if there is a disk with a hole, that is r equals to a, there are some stresses, and r equals to, say, r equals to b, the outer radius of the disk, then there are certain boundary conditions. So, if we substitute those boundary conditions, then we can get the appropriate C1 and C2 value, and then we can calculate the stresses. So, for instance, if if we consider a simple solid disk, then that is a equals to 0 and then b is the radius of the disk. Then if we look at this quantity, so this quantity 1 by r, 0 to r equals to b here. So, this r equals to, if I take b, then tr dr, this quantity if I r tends to 0, then this quantity becomes 0. So, this implies that this cannot be in the displacement solution, or C2 can be 0. So, ur should be free from the constant. So, this limit you can evaluate and then see that this goes to 0. So, now if there is a solid disk, there is no surface boundary surface traction here. So, only the temperature rise. So, there is no external force. Then sigma RRB must be 0. So, that is at r equals to b. So, this is r equals to b. So, if we put that, then we can find out C1, what is the value of C1. So, now then we can substitute this in the previous stress expression to get the surface temperature, what is that, and that leads to finally there is a constant temperature at the center. So, this constant temperature can be 0 also. So, this way we can solve some of the systems analytically. So, for instance, if we look another problem, say a sphere of a thermal stress in a sphere, so which is a three-dimensional body. So, if I look in this way. So, now from here there is a, if I take a element, so there is a tangential stress sigma Tt in this direction, and then sigma Tt in this direction. So, this has to be balanced, and then this quantity, if I take sigma r here, sigma r r, and then this is again sigma r r plus delta sigma r r. So, this is the only stresses we will observe. So, again if we put this thing in the differential equation of three-dimensional elasticity, then we get this simple formulation, simple differential equation of this form, similar to the previous case. Now, here again we are assuming that T is a function of, or temperature is a function of R only. So, there is no tangential dependence of the temperature. Now, similar to the previous case, we get the du dr is radial direction strain, and then epsilon tangential direction strain will be only u by r. So, finally, you get this form of the compliance relation. And then again, likewise in the previous case, if we substitute these compliance relation to the or if we find out the stress strain relation, then this looks this form. So, now again if we solve this, if we put this equation here, then we get a differential equation in terms of u, and then we can solve this differential equation, and again there is a boundary condition by which we can find out the constant like previous case. So, let us see how it turns out. So, for instance, if I just substitute that, so I will get a differential equation which is also, if you remember, for a plane stress plane strain case, we get similar type of equation. So, now even though this is a 3D problem, so this is, if I solve this, so I get a solution in terms of two constant, because it is a second order differential equation. So, now again if I put in terms of stresses, in terms of stresses, so this C1 and C2 will appear in the stress expression. So, now again likewise in the previous case, if I assume it is a solid disk, so then my this limit goes to 0, then again C2 can be 0. So, this quantity I can remove from the body. So, this quantity I can remove from the displacement expression. So, now once if I assume there is a solid disk, so there is, that means A equals to 0 essentially. So, here if I put R equals to B, or there is a that outer radius is B, and then the outer radius or the radius of the sphere is B, then considering again likewise in the previous case the traction free boundary R equals to B, that sigma RR has to be 0. So, this gives me the constant C1. So, now once we know this C1, and then we can write the stress expression, what will be the form of the stress expression. So, stress expression will be like this, and tangential and radial stress expression. Now, suppose we have a sphere which is uniformly heated from T0 to T1. Now, this sphere, this can be liquid or anything, means the heating through the liquid or any external heat source. So, if the temperature is maintained T1 degree, then we can show from this expression that my stresses varies sigma RR, sorry, the maximum stress can be this, and which is the compressive stress, maximum compressive stress occur at the surface. And so, T0 is my initial cold temperature, and T1 is my the temperature which is higher of the higher than T0. So, this gives me a compressive stress at the maximum compressive stress at the surface. So, in this way we can solve some of the simple problems of thermoelasticity analytically. Now, again I want to say that we have done the theory of thermoelasticity, what are the governing differential equation, what are the plane stress governing differential equation, plane strain governing differential equation, and we used stress function. Likewise, for the purely elastic case we use stress function approach. So, in the thermoelastic case also we have shown the displacement functional approach. So, this can be assuming some displacement potential functions like psi, we can solve those differential equation. But most of the solution, even for the simple cases, will be very analytically complicated. So, for ours, this our objective is not to form this analytical expression. Rather, we want to solve these equations in a numerical setup, where we use our numerical tools, for instance the finite element method, finite difference method, or even mesh free method, or even other collocation type of method, where we just discretize those differential equation in space, and then we solve the differential equation, like with the finite element method we solve for a Navier's equation of elasticity. Now there are 2-3 things that has to be remembered for thermoelastic deformation, that we are following a uncoupled thermoelasticity, where actually we do not solve the heat equation with the Navier's equation of elasticity. Rather, we follow the Duhamel-Newman Duhamel-Newman constitutive relation, and we separately get the temperature distribution, and then put those temperature into the Navier's equation to solve the system. Now there are problems, or there are type of problems where this uncoupled form of thermoelasticity is not applicable, but most of the civil engineering structure under linear regime. Linear regime means where the deformation is small, so this uncoupled form of the thermoelasticity is applicable. But since the differential equation or the analytical solution is very difficult, we go for the approximate solution through different approximate methods. So that is another part of that. Now the other part of the thermoelastic deformation is actually we can even model the residual stresses of a body through the thermoelastic formulation. For instance, if you when the steel members we receive, it comes from the mill, it contains the residual stresses essentially. So what is residual stress? Residual stress are essentially the initial stress in the body, because the milling process gives you some permanent deformation which is embedded into the members. So this residual stress can be very important in a member where actually if you have a crack or something, some damage in the lifespan of the member, then this damage and crack propagate very differently if it has inbuilt residual stress while coming out from the mill. So this thermoelastic deformation can also model this residual stress model. So this goes to again the advanced topic, which we will not discuss here. So but it is important to know here that even though residual stress that can be modeled with the same equation of this thermoelastic deformation, the equations which is essentially applicable for the thermoelastic deformation. And another important part is that even if you look at this differential equation, this acts as a body force in the body. So if you remember the Navier's equation of elasticity, which is sigma divergence of stress plus B or F equals to 0. So this if this contains a thermoelastic deformation, which is in terms of alpha delta T for an isotropic material, so this essentially goes to this side. So if I again write this, if my thermoelastic constitutive relation is this, C is my constitutive matrix, then epsilon is my total strain, then epsilon is my thermal strain. So then this if I substitute and if I take body force is 0, then we can easily show that this term C epsilon, so divergence of sigma C epsilon is essentially, so this is inner product of two tensor. So this goes to this, so divergence of C into epsilon star. So this epsilon star is the thermal strain. So this if I say this is my residual stress or sigma 0. So, which is, if I know, then this problem can be so residual elastic strain is developed in the body. So, essentially this part is the body force which acts in the differential equation. So, that is all. We have solved our objective of this module was to solve some of the, to know that first the theory of thermoelasticity and what is uncoupled thermoelasticity especially, and then we did some of the plane stress plane strain formulation, and then we have solved some of the analytical examples by which we can solve some simple problem with simple geometry and boundary condition. But major emphasis is actually the solution of these equations are mainly done with the approximate methods, because analytical methods we have several difficulties in obtaining these analytical functions of the displacement. So, that is all for this module. In the next module, we will start another aspect of the elasticity, which is very similar to the experimental stress analysis, is known as the photoelasticity. Thank you.